In this video, we're going to talk about uncertainty and error as it pertains to physics measurements. So, when we think of an error, we think of a problem or a mistake, but in physics it has a different meaning. So it's not that you made a mistake doing something, it's that every measurement you make has intrinsic uncertainty to it. Physics is a science which is based on measurement. Part of what we do is we compare theory to experiments, we compare other experiments with each other, and we also measure physical constants. But the best we can say when we make a measurement is that we have a value within a certain range of uncertainty, and that our measurement either agrees or disagrees with a theory based upon whether it's within that uncertainty. And what we'll do today is talk about that measurement of uncertainty, and we'll talk later about how we know whether experiments agree or disagree. So this uncertainty is often referred to as measurement error. Again, it's not a mistake, but it's the intrinsic uncertainty in our measurement. And these errors come in two different kinds, random and systematic. And so we'll talk about mostly today random, but a little bit about systematic error as well. So every measurement you make has a limited precision, and that precision results in what we call measurement error. So but you can also have, even if you make a relatively precise measurement, it can be off if the instrument, for example, is improperly calibrated. So errors again fall in two general types, random errors and systematic errors. Random errors come from the limited intrinsic precision of your measurement. It can come from the measurement device, how good can you read a ruler, how well can you read a stopwatch, how well can you measure something with a caliper. They can also come from your ability to measure with the device. For example, even if your stopwatch has a great precision to it, there's a certain reproducibility associated with the reaction time, and with random error comes from just not clicking the button the same every time. Systematic error, on the other hand, could be that if your stopwatch timing is just wrong, it doesn't agree with all other clocks. So you can generally often calibrate out uncertainties due to systematic error if you know what they are, but random errors we'll see we can beat down by taking multiple measurements of the same thing. So let's talk about intrinsic precision. Consider the ruler here. So if you look at this ruler in the picture, the smallest markings on this ruler are a millimeter. So I can generally read something to at least a millimeter, but I could probably read it to within half a millimeter. I could say which one line does it line up with to half a millimeter. If I look at the stopwatch over here, the last digit is 1/100th of a second. So I could say that the precision of the stopwatch could be read to within 0.005 seconds. So that's the half width of the smallest unit. The question is, could you, even though I can record something to 5/100ths of a second, do you really think I could measure something to 5/100ths of a second? My bet is the answer is you can't. So that the precision of the device isn't the limiting factor, it's your ability to record and press the device. So oftentimes we think if we have a digital device, it's intrinsically better than an analog device. So if I, for example, look at these speedometers in the picture here, if I look at the old analog speedometer here on the car, the last digit, the white digit here, is the 1/10th of miles. And if I look at the digital one on the right, I can look at the odometer here, or the trip setting down here, and I can see where it says 092.3, and that's the trip setting. And so the last digit is also a 1/10th of a mile. But you can look, if you look at the one on the left here, you can read it to much better than the last 1/10th, because here you can see it's between 7 and 8, and you could guess that it's almost precisely 7.5 miles. Where here you have no better than the last digital precision. It doesn't mean it's not recorded better, so having an analog device isn't necessarily better or necessarily worse, and what may matter is how well they're calibrated. Actually here, for example, again, looking at the speedometer, on the left you can see that I'm going 63.5 miles an hour, and on the right, on my heads-up display, you can see that it can only tell that I'm going 63 miles an hour. You can also tell the speed limit's 55, and if there was a policeman there, he might have a more precise measuring device, a radar gun, that could give me a better exact readout, even though I hope he doesn't. Okay, so let's talk about making measurements. Oftentimes when we make more than one measurement, we want to compute the average of those measurements. And most of us know what the average means. To take the average of a group of numbers, it's written as, in physics notation, x bar, where x bar means that you take the sum of the numbers and divide by the number of measurements you've made. So for example, the average of the numbers 3, 4, and 5 is 4. You can see that's the average, but you get that by adding 3 plus 4 plus 5 and dividing by 3, which is 12 divided by 3, which is 4. So average is the average. The deviation, on the other hand, is if I want to compute the deviation of a set of numbers, I can compute the number x of my individual measurement minus the average. I will also sometimes take, now this quantity will almost always have a sign which is either positive or negative. The number can be larger or smaller than the average because the average will be the mix of those two. The deviation squared, on the other hand, is always a positive number. So we're going to compute a couple of other numbers here, which is the mean squared deviation, which is the deviation squared, and we'll compute the average or mean of that. So to compute the mean of anything, you add the numbers up and divide by n. So in this case, we add up the squared deviations and divide by n. We can also compute something called the root mean squared deviation. So that's lots of words, but what it means is the square root of the average squared deviation. So it's kind of funny because we're taking the square root of something we've already squared, but there's a reason for this, which is that what we're doing is we're taking the square root of the deviation, the average deviation. So this is a always positive quantity, and we're taking the square root of it after we've summed them up. Now, the RMS is a good measure of the uncertainty of individual measurements. However, if we don't know the true mean of the distribution, we find out that we actually use a slightly different formula, which we've often called the standard deviation. Now, most of you have heard of the standard deviation. The standard deviation is very similar to the RMS, but instead of dividing by n, the number of measurements, we divide by n minus 1. And the reason for this is we've used up what we call a degree of freedom in figuring out what the mean is. So if we take 5 numbers, we have to compute the mean from those 5 numbers. If we knew intrinsically what the mean was, we wouldn't do that. So, as an example, we had a student measure 3 swings of a pendulum 25 different times with a stopwatch. So you see the data here on our spreadsheets. Here are the different trials, and here are the different times. And what you can see is that they have a spread in the numbers. As a matter of fact, if we just kind of go over here, we can see if we highlight them, we can see that the lowest number is 5.78 seconds, and the longest number is 6.16 seconds. So the full spread of this thing goes from 5.78 to 6.16 seconds. But they're pretty well centered around sometime around 6 seconds. So first off, we could compute the mean time. So how would we get the mean time? Just like we described, we would sum up the numbers, which we can do by saying sum of this column, and that's 149.2, and we take this column and divide it by the measurement number, which is 25, and that will give us the mean of 5.98 seconds. So we've seen we have a width which goes from 2 extrema to a mean of 5.98 seconds. Now, another way of doing this, of course, is just to use the function called average. So if I take the average, right there, I also get 5.98 seconds. So I can do it by summing them up manually and dividing by the number, or just taking the average. Now, I can compute this number we call the deviation. So what is the deviation? The deviation, for example, in this case, is if I take the difference between this number and the mean. So minus the mean. Now, I'm going to want to copy this formula, so I'm going to want to fix that value of that cell E4, which is the mean, which I could do by naming it, or I could press F4 if I had a Windows machine, but I have a Mac, so I press Command T, and that puts dollar signs in front of this. And so now I have the deviation. If I pull this all the way down to here by the corner, I've copied this down and I get the deviation from each one of these from 5.98. So 6 is 0.02 larger, and you can see how this all varies. Fine. Now, I could take, if I wanted to, the deviation. Now, this, by the way, if I take the average of this column, you can almost get this, that the average of this column, almost by definition, is guaranteed to be 0, because we've computed the average by minimizing the deviation. So if I take the average of this column, it comes out to be 0, as it should. So I don't learn anything about the width by taking the average deviation. If I want to learn something about the width of this distribution, I need to take the average deviation squared. So that's easy to do. I say it's equal to this cell squared. And then I can even pull off a quicker trick here by just double clicking the little thing here, and that automatically pulls down my thing right down the bottom. And so now I have the deviation squared. And if I wanted to compute the sum of this column, I could just simply say equals the sum of this column. Okay, so that's the sum of the squared deviations of this thing. So if I wanted to compute the root mean square, what I would do is, let's go back and think of those words a minute, root mean square. So I want to take the square root of the mean of this distribution. This is the sum of all the squares. So I would say equals the square root of this number divided by, in this case, 25. Okay, and that will give me the root mean square, which is 0.092. Now, remember, the standard deviation was similar to the root mean square, but the difference here was I took, for the standard deviation, I said it was equal to the square root of this number divided by n minus 1, which is 24 in this case. So you can see for these measurements, these are very close to each other in terms of numerically. So this is 0.092, this is 0.094. So the standard deviation is, we should use, since we didn't a priori know what the mean of this distribution, we should use the standard deviation, but the RMS is not very different. So this characterizes the width of this distribution. So if I were to make a histogram of these numbers, which I've done on another spreadsheet, and we look down here, we can see this is the histogram of the times, and we can see that we got from the previous sheet the RMS, which it was 0.092, and the standard deviation was 0.094. So we can see that this characterizes something about the width of this distribution. So let's go back to the question of what is our uncertainty? When we read a ruler, we often get the same answer. So we will generally look at this and we'll measure, if we measure the length of something, we'll just generally say, well, we got the same thing. Sometimes we'll get a little different, but we often get the same answer. So using the ruler, we generally assume the uncertainty is estimated to be half the smallest scale, which in this case is 0.5 millimeter on this ruler. However, using the stopwatch, as we saw before, the smallest scale is 1/100th of a second. But we just saw that using this watch, our student, making a measurement of the same quantity, got a standard deviation which was 0.94 seconds. So more than 9 times larger than the smallest unit. In this case, we use those multiple measurements in the data to estimate what the uncertainty in that measurement is. So we use the standard deviation to characterize the uncertainty obtained by taking multiple measurements of the same quantity. This was our formula for the standard deviation, and we can write that our best estimate for the quantity is the average value we got plus or minus sigma, the standard deviation. So what does this sigma tell us? Well, sigma is often used in terms of the Gaussian distribution. The Gaussian distribution, or bell curve, is something which you're familiar with from grading and other places like this. It's used in a lot of things. And in a moment, we'll talk about why the central limit theorem tells us this is the right distribution to use. But let's look at this distribution for a second. What we see is that it tells us that 68%, 68.2% to be precise, of the measurements fall on this curve, the data fall within plus or minus 1 standard deviation of the mean. This particular one has a mean of 0, but whatever the mean would be, we can write the formula as some normalization here, e to the minus x over x average. So this is the deviation squared over 2 sigma squared, and this is the exponential. So this says that 68% of our measurements should fall within 1 standard deviation and 95% within 2. Now, I like to joke about this. The students are very happy if their data falls within 1 standard deviation, if 2/3 of their data falls within 1 standard deviation. What they're not happy about is 1/3 falls outside that. But 1/3 should fall outside of 1 standard deviation. So we'll come back to that a little bit later. But let's talk about why this Gaussian distribution is meaningful when we take data. So there's this thing called the central limit theorem, and what it establishes is that when you take independent random variables, in our case our measurements, and we average them, they tend toward a normal or a Gaussian distribution, even if the original variables themselves are not normally distributed. You say, well, why should my measurement of the time be normally distributed? It may not be, but provided you take averages of the data, you will get the distribution of the average will be distributed like a Gaussian. So let me show you an example. Okay, let's take an example which illustrates the central limit theorem. Let's pick something which has a completely flat distribution of sampling, rolling a die. We know that the odds of rolling a die of getting a 1, 2, 3, 4, 5, or 6 is the same if the die is well balanced. And it turns out that the average value you should get, the average score you should get rolling a single die, is the sum of 1, 2, 3, 4, 5, 6 divided by 6, which is 3.5. So if we take this thing, and just as an example, so we know that if we plotted that and we did it as many times as you wanted to get a completely flat distribution. But what if we took two dies and averaged them together? So we rolled it once, rolled it twice, averaged them together, and then we did that 500 times. We plotted that distribution. That's what this graph on the right looks like. So we've taken 2 die and we've taken the average of 2 rolls and we've plotted them. And you can see it's starting to already take on a Gaussian shape. Now, if we take 5 rolls and average them together, that's this bottom plot, it looks more Gaussian. 10 rolls and average them together, and then do that 500 times, you get this plot, and here's 30 rolls, and you can see it really has a nice Gaussian shape. It approaches a Gaussian. So the question is, if I take more measurements, will my histogram get narrower? And it turns out the answer is no. My histogram doesn't get narrower. My distribution doesn't get narrower. The points still have the same intrinsic sigma they've always had. So what is the advantage of taking more points? Well, let me show you an example. Here I picked 50 points from a Gaussian with a sigma of 3 and a mean of 0. So that's this plot on the left. If we look at this plot, it kind of has a Gaussian shape, but it's a little raggedy, but I only picked 50 points. If I now take a histogram with 250 points, same width, same mean, you can see it's centered around the same place, but it's looking more and more Gaussian. And if I take 1,000 points, it looks much, much more Gaussian, but it has the same width. It has a sigma of 3. So if we look at this, we can say that 2/3 of the data should be within plus or minus 3, and that's what you find when you look at this plot. But it turns out, so what's the advantage of taking more points? Well, I may not have a narrower distribution, but I know the average of those points better. So let me show you that. So it turns out while the width doesn't decrease, you have a better estimate of the mean of the distribution. So the sigma of the mean, which is the standard deviation of the value you get for the mean of the distribution, is equal to the sigma of the individual events divided by the square root of n. So this mean, the sigma of the mean, gets narrower as the number of events gets larger. So we can find a better estimate of the true value of the distribution. So let's say I had a distribution with a sigma of individual points of 0.1. It wouldn't matter how many points I sampled, I would always get a Gaussian with a width of 0.1. If I take 100 points, I can know the mean of that Gaussian to the individual sigma, which is 0.1, divided by the square root of 100, which is 10. So I would get the sigma of the mean as 0.01. So can I continue to do this? The answer is yes. If I would like to get a factor of 10 better, I would have to do, on the other hand, a factor of 100 times more samples. So that would be 100 times 100, which would be 10,000 more measurements. But if I took 10,000 more measurements, I would get a sigma of 0.1. So to kind of summarize, let me show you an example. Go back to our data here for example. So let's look at the one where I picked 50 points. And if I can actually computed the average of this distribution, it turned out to be 0.36, even though I picked from a distribution which had a central value of 0, but it has a Gaussian width. Sigma over root n, estimating for this, is 0.42, root n being 50. So this is within one standard deviation of the actual true value, which is 0. So it would be, so if we look at the 250 histogram point, I get an average which is closer to 0 to start with, 0.13. And again, sigma over the square root of 50 says I should know this to plus or minus 0.19. And again, a good fit. And the same is true with 1,000. Here, this particular one, it isn't always going to be within one standard deviation, but 2/3 of the time it will. So here I got an x value, an average x of 0.05, and sigma over the square root of 1,000 is 0.09. So you can see here, I know the mean 4 times better, but I'm really getting a better estimate of the mean. So that's why we take multiple measurements, and that's what the standard error of the mean means.